Elisa. Thank you very much. So once again, let's start because it's easy for me to classify recording on YouTube. Okay, now we just recall what a stochastic integral is from intuitive viewpoint. It's a profit when WT is interpreted as a price of an object, let's say of a cup. Have an object, yeah, of a cup. Say price of an object at time t, and AT is considered as number of objects, quantity of objects, of shares, I don't care, quantity of objects at time t. And this is a profit. Basically, we showed how we may calculate a profit, final wealth minus initial wealth plus investment minus investments or plus payoffs during the period. Okay, so let's go back and consider an example. One more. I have AT is described like 2 if t is less than 5, and is described like 1 plus w1 w5 squared if t is greater than 5. And my question is calculate integral from 0 to 4 au dwu, calculate, so this will be a, b, integral from 0 to 10 au dwu, and calculate general case from 0 to t au dwu. Okay, let's go. Okay, first, this a is interpreted as a quantity. So this is my t, this is AT, it is 2. And then at moment t, it jumps. It may jump below or it may jump above current level. I will draw one case, but other case is also possible. So this is 1 plus W5 squared. So it may jump above current value, then I should buy this asset, or it may jump below and I should sell this asset. Okay, first integral. What is your profit of AU dwu if we change u from 0 to 4? What is your profit? Imagine that your grandma
W4 minus W0.
You have 2 cups. You have 2 cups. You have 2 assets. Like I don't know. Where is the second? You have 2 cups. So your final wealth is 2 times W4 because you have 2 cups, and each cup has a price W4. Your initial wealth is you have 2 cups. Each cup is worth W0, and it's 2 W4. Okay.
Where did we state that WU is the winner process?
It's our agreement. WU will always denote winner process, unless explicitly state otherwise. Yeah.
Okay.
We should state W winner process. Okay, the second one, integral from 0 to 10 AU dwu is.
Oh, may I ask a question?
Can you please clarify the previous point? How did we get 2W4?
Imagine that your grandma left you 2 cups. The heritage. I have 2 cups. And you have 2 cups. I have non-identical, but your grandmother left you a big heritage of 2 cups. And you are just holding them. You are not buying, you are not selling, you just have 2 cups. And what's your profit if you just hold them from 0 to 4? Okay. What was your initial welfare? Your initial welfare was 2 cups times the price of a cup W0. Your final welfare, the price changes. You have 2 cups, you do nothing, but the price changes. So your final welfare will be 2 cups multiplied by final price W4. Okay, so 2 cups multiplied by final price of each cup is 2 times W4. Your initial wealth so is 2 times W0, and so final wealth minus initial wealth, I get my profit. Okay.
Okay, I see. Thank you.
Yeah, we have 2 cups, and we do not buy new cups. But in the case when we integrate from 0 to 10, there will be one transaction at time t equal to 5. And so our final welfare will be, what will be the amount we have? It will be 1 plus W5 squared. I multiply it by price by W10 at final moment minus, I subtract initial welfare. Initially, I have 2 cups. My grandma left me W0, but in this case, I'm doing transactions. So I need to subtract how many cups should I buy? I should buy 1 plus W5 squared minus 2, how much I would like to have, minus how much I have, and I multiply by which term?
W10.
Sorry?
Wait.
Yeah, Elisa is
W5,
right.
W5.
Yeah, by W5. Always the structure is the same. Always it's something like quantity times price, quantity times price. Oh, this is delta quantity, but it's quantity times price. Okay.
Yes, clear. Thank you.
And finally, in general, we will have a stochastic process if I integrate from 0 to t. So my final answer will be integral from 0 to t, au dwu. I will have either 2 times w t if t is less than 5, or this big sum like 1 plus w5 squared times w t minus what initial wealth is 0 minus w squared minus 1 times w5 if t is greater or equal than 5. Yeah. Any questions?
Yeah, may I ask a question, please?
Yes.
So we have integral and we over Wiener process.
Yes.
Can we take integral over just any random process?
Not any. To make, so we will not define it rigorously. So our course is, so we can define stochastic integral for wide range of processes, but not for everyone. We need to avoid some some bad processes with too many discontinuities. So because here, when you take formal definition of a stochastic integral, you need a sequence of sums. You need to subdivide for continuous time. You need to subdivide a big interval into small subintervals. And if your process has high probability of jumps, then the definition will vary depending on whether you take the moment with jump or not. So the answer to your questions, not for any, but for a larger class of random processes. Yes.
Okay, thank you very much, Professor, for the answer. So, like, just if to further ask a question on the last question, does that imply that in this case, if you have an integral or any processes we have an integral on is a continuous process?
In our course, we will work. Yes, we will integrate. We will work with continuous processes. There are some more requirements, like so there are more technical. So we will not. Here will be a little gap. We will not define stochastic integral rigorously. We will give some rules how to calculate them, but it's a little bit difficult with stochastic random sequences. There are many modes of convergence. We need one mode of convergence, and it's a little bit tough to study them. So we need more time, but our time is limited. We have 6 lectures for the whole course of stochastic calculus. So no, we will. Okay. I will try to make something rigorous, but I can't with
time restriction.
Okay.
Okay.
So
thank
let's
you.
Go.
So sorry, do I get it right that if we sell, nothing would change?
Sorry.
Here we buy additional units, but if we sell, nothing would change, right?
Yeah. If we interpret as a selling, then you will change 2 signs, because if it was, let's say, so to buy 5 units, you may like I sell -5 units. Yeah. So if you have interpretation that you basically sell, then what does it mean? If you sell, this is negative. Yeah. If you sell, and that's okay. Yeah. It's added. Sorry. And so nothing changes at all. So you may write something like plus as alternative. Yeah. You may write plus
1
yeah, plus 2 minus 1 plus W5 2, and the result obviously will be the same.
Yeah, thank you.
So it doesn't matter. So okay. Now our main goal will be to almost rigorously calculate integral from 0 to t wt d double. Sorry, I can't have same index. dwu. So our goal is to calculate this stochastic integral. So basically, it has no good meaning. It's a strange. You may consider it as a very strange trading strategy. So this is the price. Price is here WT. So it's a price of an object. Just ignore that it may be negative. And this is quantity. Quantity is also given by WT is a quantity. So it's the same. So it's a little bit hard to make a copy, but believe me, I've tried.
So these are 2 same winner processes, right?
Yeah, yeah. If I'd like to introduce another one, I will like W star or W second. Yeah, the same. So this strange trading strategy means that at moments when the price is 5 rubles, I should have 5 shares. When the price is 10 rubles, I should have 10 shares. If the price is 1/2, I should have 1/2 of a share. Okay. Could you please explain what do quantity 1 plus? It was our trading strategy. So it was a question what quantity means. So my question. So this is my strange. This is given. This is my trading strategy. I have 2 shares. Then I have 1 plus W5 squared shares. Okay, in this case, the number of shares I have is exactly equal to the price. So it changes continuously. So I should do transactions every moment of time. I buy a little bit, I sell a little bit, and so on. So we need to consider a limit. We need to consider a limit of sequence of random variables. So let's describe the mode of convergence we need. So when you speak about numbers, there is only one convergence. So if you have any sequence, A1, A2, A3, and so on, this sequence can converge to the number A or do not converge to the number A. But when we speak about random variables, there are different modes of convergence. X1, X2, X3, X4, and they may converge to X in many senses. They may converge in L2, they may converge in probability, they may converge almost surely. There are some more modes of convergence. I will need, for stochastic integral, will need convergence in L2. What does it mean? Definition. We say that the sequence x1, x2, x3, x4 converges in L2 to the random variable x and x number k are all random variables. If first expected value of x I squared is less than infinity, expected value of x squared is less than infinity, and second property, expected value of square difference tends in normal sense because expected value is a constant and we have only one sense for constant convergence, tends to 0. So this is a definition. You may just recall that this is different from convergence in probability. Sequence x1, x2, x4, 3, 4 converges in probability to x if for all epsilon greater than 0 probability that x I differs from x more than by epsilon, this probability should tend to 0. So there are many modes of convergence and they are different. So I will provide you only one example to show that the same sequence may converge in one sense and do not converge in other sense if we speak about random sequences. When we speak about numeric sequences, there is only one mode of convergence.
Excuse me.
Yeah.
If there was L in the third power, then we would have expectation of xi in the third power is less than infinity, yes?
Absolute value.
Absolute value of
Different.
x in the third power.
No, absolute value xi minus x.
Wait a minute. If L is in the power of 3, then we have
Absolute value power of 3.
Is mathematical expectation is less than infinity, yes?
Yeah.
Okay.
You add absolute value to avoid the confusions when so to avoid something that is compensates positive and negative. So you add absolute value and you put 3 instead of 2. But you need to add absolute value. In the case of 2, you don't need to add absolute value. Okay, so let's continue. So I provide an example that shows that with random variables and sequences, yeah, less than infinity means finite. Example, we toss a fair coin, infinite number of times. Xn is equal to 2 to the power n if the sequence, the toss, the first n tosses are and 0 otherwise. And my question, first question, just find the distribution, of xn. Second question, check whether xn converges to 0 in probability. Check whether xn converges to 0 in L2. Basically, that's all. I only would like to show that there are many modes of convergence for random sequences. I don't like to go deep into the link between all the modes of convergence because I will use only L2 convergence. Okay. What's the distribution of xn? Xn can take values 2 over n and 0. So what are the probabilities that xn is 2 to the power n? What is the probability? What are the probabilities?
2 to the power of minus n.
Yeah, 1 over 2 to the power n, and I have 1 minus 1 over 2 to n. Okay, so A is done. Let's check convergence in probability. B. Let's calculate probability that xn minus 0 is greater than epsilon. But xn is positive or 0, so it's just probability that xn is greater than epsilon. Okay, I don't know the value of epsilon, but in any case, this probability is less than 1 over 2 to the power n, because it depends on the number n. Explain why. Because I have a fair coin. Believe me. I have somewhere a fair coin. And if first n tosses are ahead, or n tosses, n first tosses, that means head, yeah? It happens with probability 1 over 2 to the power n, yeah? Right. That's okay? Okay, and this tends to 0. So xn converges to 0 in probability. Now let's check C. What is the expected value of xn minus 0 squared? Expected
I'm sorry,
value.
Professor, shouldn't we say here that the probability tends to 0 as n goes to infinity?
Yeah. Yes, obviously. We cannot tend n to 0 because n is a number of tosses. Yeah. Yeah, I meant it. Yes, if you'd like to be a little bit more. How did you obtain that probability is less than? To be positive, to be greater than epsilon, you need at least to be positive. So probability of xn greater than epsilon. I don't know the value of epsilon. Maybe epsilon is 1 million. Nobody restricts big values of epsilon, but this is less than probability that xn is greater than 0. And that probability is given here. Okay, Ruslan? Okay, so now with expected value, xn squared. So I have 2 to the power n squared multiplied by probability by 1/2 to the power n plus 0 squared times something. And I will have 2 to the power n. And when n tends to infinity, this doesn't go to 0. So my conclusion that xn does not converge to 0 in a sense in L2 sense. So my main point with this example is there are different modes of convergence, and the same sequence may converge in one sense in probability and do not converge in other sense. Okay, the example is clear.
Yes, clear.
Okay, now let's go back to our goal. I remind you that our goal is to calculate integral from 0 to t w d w. To achieve this goal, first we will build a discrete approximation. So first we will build discrete approximation. What do I mean by discrete? I will divide the whole timeline from 0 to t into n equal intervals. Each interval will have n equal intervals. The length of each interval will be t over n. Okay. This will be only one point when I deviate from the general definition of stochastic integral. In general definition of stochastic integral, these intervals may have different lengths, and the only requirement is that the maximal length of an interval goes to 0. And they may be different in the true rigorous honest complete definition of stochastic integral. But for simplicity, that's only one point when I will deviate, where I will deviate from honest definition of stochastic integral. I will suppose that the line is divided into equal intervals. Otherwise, we have a rigorous procedure to calculate stochastic integral. So we will subdivide into equal intervals and take limit in L2. In general definition, which you may find in books, maximal length should tend to 0. Okay. Yeah.
Yes.
Okay, let's go on. Let's calculate approximation. Approximation IN. That means I will trade my asset only at these moments of time. No, I will not trade my asset continuously, but I will trade my asset at these discrete moments of time. So I trade only at t over n, 2t over n, 3t over n, and so on. Okay. Okay, if I trade only in these moments of time, then what is the quantity I will have? Quantity. When I start, the price is W0, and I should have W0 cups. When the moment of time is t over n, how many cups should I have?
W2.
Wt over n. Yeah, it's not W.
Oh, yeah, yeah.
Yeah, this is quantity. So I should have Wt over n. At the second transaction point, how many cups should I have?
W2T over n.
Exactly, Wt2 over n, and so on. So let's calculate In. My initial welfare, so my final welfare will be Wt times Wt, price times quantity. It's my final welfare, minus my initial welfare, minus W0 times W0, okay? Minus investment that I made. Imagine the first transaction point. So imagine the first transaction point. It's point 1, point 2. It's not time, it's number. Yeah, it's not, let it be number 2, number 3, number 4. Okay, at first transaction point, how many cups should I buy? I have W0 cups. I want to have Wt over n cups. So I should buy
The difference.
the difference, Wt over n minus W0 times what is the price of each cup at this moment of time?
Wt over n.
Wt over n minus. At the second transaction point, I like to additionally buy W2T over n minus what?
T over n.
Minus Wt over n multiplied, which is the price?
2T over n.
W2T over n minus, and so on for each trading moment. Any questions?
Yeah.
Because now we will just tend n to infinity and calculate limit in L2, okay? So basically, we are on rigorous ground with unique exception. In my approximation, I take subdivision of big interval into equal small intervals. In true general definition of stochastic integral, it's a little bit trickier because you need to consider all possible subdivisions when the biggest chunk, the length of the biggest chunk tends to 0. Okay, so that's one difference. Otherwise, we are doing everything rigorously.
Can I please ask a question?
Yeah.
Why do we in this in second period subtract Wt over n and not W0 once again?
Because we have already. So if imagine that you have one cup from your grandma. At the first transaction, you buy the second cup. How much should you buy at the second transaction point if you'd like to have 3 cups? You should buy one more.
Yeah, got it. Thanks.
Okay, let's move on. So our In is just Wt squared minus sum I ranging from 1 to n Wit over n times Wit over n minus I minus Yt over n. So I have just written the same thing with sigmas, but basically that's price times additional quantity to buy. This is final welfare. Okay, just a little bit of practice with a theorem. I have a good theorem that says that if random sequence R1, R2, and so on has the following properties. First, expected value of Ri tends to mu, and variance of Ri tends to 0. Then almost all limits are defined, all stochastic limits, something like R1, R2 tends in L2 to mu. They also tend in probability to mu. So in this simple case, when the variance decreases, so what does it mean intuitively? The variance decreases. It means the random variable is less and less random, is more and more like a constant. But if expected value goes to mu, then the random variable is more and more like a constant mu. The formal proof is based on Chebyshev inequality. I will omit it, but if you'd like, you may try to prove. It's not so hard. Chebyshev inequality is used in the proof, but I will use this theorem. Okay. So now our goal has much simplified. I recall that we'd like to calculate this integral VWU dWU. We have simplified our goal. Now we just need the limit in L2 of IN. Okay, so basically we need to calculate only one limit in L2. But it's a little bit hard limit. Yeah, it's not so easy. So I would like to just calculate something that is simpler and then go back to IN. Okay, so I hope I have explained goal. The goal is to calculate first stochastic integral almost rigorously. The one trick, one small gap that is not formal definition. So I take equal length segment. So I would like to calculate the limit in L2 and just a little bit training before. Just a little bit training before. Because this integral is a little bit hard to take from the start, so just some training. Let's consider something like Kn, which is the sum of T over n times Wt over n minus W I minus 1 T over n. So it's almost like our, but with first Brownian motion replaced by a constant. So first calculate this guy. Second, K, let's say Mn is just Wit over n minus W. I'm a little bit bored. Let's introduce some notation. So that will be our training. And then we will tackle our original problem. And finally, we will calculate our goal. So just a little bit training. I'm a little bit bored to write this big omega, this big Wi minus 1. So I will introduce Vi is just Wit over n, and Wi minus 1 is just Vi minus 1 is just Wi minus 1 times T over n. Just notation to simplify because I'm a little bit bored to write Wit over n. Okay. We
Sure.
go. Okay, so just a small question. What is the value of V0? What is the value of Vn?
First is 0.
First is W0, but W0 is Wiener process, so it's 0. And Vn is?
Wt.
yeah, is WT. Okay, notation is clear. Just to simplify a little bit, yeah, to avoid the long, to save ink and energy, if you right way.
Yes, yes.
Okay, so let's work with Kn. So Kn is just the sum T over n Vi minus Vi minus 1. What is the distribution of Vi minus Vi minus 1? Which is a distribution according to the properties of Wiener process. The delta of Wiener process, the increment
It's normal.
is normal.
0
0
and 1.
not 1, because time difference.
T
So,
minus x.
T over n.
Yeah, T over n, because it's I minus 1 T over n. This is Wi T over n. And time interval in seconds, in minutes, in hours, not because this I is on this, on where it is. Yeah, I is a number. Yeah, Vi means, so I is a number of an interval, but the time is IT over n. And to calculate variance of Wiener process, we need time and not number of interval. Okay, so it's WIT over n minus WIT, oops, sorry, I minus 1 T over n, and it will be, if I take time difference will be IT over n minus I minus 1 T over n. It will be just T over n. Okay, the variance of Vi minus 1 is clear.
Clear.
Okay. Let's
Excuse
continue.
me. How did we obtain that the expected value of the difference is 0?
We have properties of Wiener process Wt minus Ws by the definition of Wiener process
Yes, I see.
is normal with T minus S.
Mm-hmm.
So this is just definition of Wiener process.
Mm-hmm. Thank you.
Okay, now let's calculate our second limit in L2. We have Kn, which is sum of scaled differences of Wiener process. This thing is normally distributed with mean 0 and variance T over n. So expected value of Kn is
0.
0. The variance of Kn is a little bit subtle, yeah, because we need to remark
T squared over n.
we need to check whether these differences are dependent. So first, we need to check whether they are dependent. Yes, basically they are independent, and we can say that it's sum of T over n squared times variance of Vi minus Vi minus 1. Yeah, Vi minus V. So these differences are independent, but it's let's check why they are independent. So these random variables are independent. And so we can replace the variance of a sum by sum of variances, and it will be sum T over n squared times T over n will be n times T cube over n cube will be T cube over n squared. And when n tends to infinity, this tends to 0. Okay, I will explain a little bit why these differences are independent. So I will consider, let's say, 0, 1, 2, 3, 4. I'm here. Current time is 4. And let me consider what is V5 minus V4. It's VW5T over N minus W4T over N. This is time. This is segment number times 0, T over N, 2T over N, 3T over N, 4T over N, 5T over N. This is future increment for me. And by the properties of Brownian motion or Wiener process, future increment is independent of everything I know. But what do I know? So I know my information is sufficient. What do I know? I know WT over N, I know W2T over N, I know W3T over N, and all W's in between. I know W4T over N. And so future increment is independent of everything I know. I may combine what I know in every way. Take the differences, take the sum, take the product, logarithm, cosine, every function. I can take every function almost in honestly measurable function. Yeah, I can take any continuous function, and what I know will be independent of future increment. So that's why this future increment is independent of all past increments. Okay.
Yeah, sure.
So our conclusions for K, our small example, expected value is exactly 0 and variance tends to 0. Our conclusion, the sequence of Kn tends to what?
To 0.
To 0. In L2, in probability, because variance is less, so the sequence of random variables K1, K2, K3 is more and more like a constant, and expected value is 0, so it's more and more like a constant 0. Okay, with Kn we have finished, yeah?
Can I please ask a question?
Yes.
So why, when we calculated the variance and opened the brackets, why did we put just the variance of Vi? There should be also variance of Vi minus 1, and we said that covariances would be 0 because independent, but there shouldn't be two variances.
Why two variances? I have n terms, and I sum n variances. So I have n variances here. So it's a sum.
Sure. Got
So
it.
variance, I have n terms in the sum. So I take variance of n terms. One term is delta of Vi minus Vi minus 1.
Yeah, thanks.
Okay. Let's consider our second example, the sequence Mn. Mn is a sum of Mi minus Vi minus Vi minus 1 squared. Once again, I need to calculate expected value of Mn. It will be n terms times expected value of V1 minus V0 squared. And I can calculate its expected value of what is V1. V1 is just Wt over N squared. What is the expected value of Wt over N squared?
It's T over N.
Yeah, exactly, because it's just variance of WT over N. Exactly. Thank you. It's N times T over N, it's T. Okay, what is the variance of Mn? It will be N times variance of V1 minus V0. It's N times variance of WT over N squared. But let's recall that WT over N has which distribution?
Normal.
With
0.
yeah,
T over N.
yeah, exactly, with mean 0 and variance T over N. So I will use standardization. So WT over N, I may represent it like square root of T over N multiplied by some Z, where Z has normal 0, 1 distribution. Okay, if I multiply by square root of T over N, then variance will be multiplied by T over N. Yeah, any questions?
Yes,
Just
sure.
don't be shy. And I plug in my calculations. So I have variance of Mn is N times variance of WT over N squared. I plug in, as I promised, square root of T over N times Z squared. It's N times T over N squared times variance of Z squared, where Z has normal distribution with mean 0 and variance 1. I don't care about this value. I don't care because when n tends to infinity, this will be 0. Okay?
But how is it possible to find the value of variance of Z squared?
You may just integrate, or we will provide you. So I will provide you a way using Ito's lemma. There are many ways to calculate this value. The most, I think, basic is to just integrate. So variance of Z squared is expected value of Z power 4 minus expected value of Z squared. And to calculate this, you need to take integral to the power of 4 f and z dz, where f is a PDF of a standard normal. So you may just integrate. I will provide you another way, but a little bit later. But
May I ask a question?
Yeah.
But can't we substitute Z square with something that is distributed as chi squared,
Yes,
with the degree of freedom 1?
Yes, you may, but I don't care about this value. Yes, you may. You may say that Z squared is S, where S has chi quadrat, chi squared distribution with 1 degree of freedom. Yeah, you may.
Thanks.
Okay, what we have discovered, expected value of Mn is T, variance of Mn tends to 0. Conclusion that the sequence itself tends in L2 to what?
To T.
To T. And in probability too. Mn tends in probability to T. Because in many cases, sequences of random variables converge in 2 modes simultaneously. Yeah, but sometimes, as we have seen, the sequence of random variables converges in 1 mode, but not in the other one. Okay. So
sure.
Now let's look a little bit once again at Mn. Mn is just sum of vi minus vi minus 1 squared is just sum of vi squared plus vi minus 1 squared minus 2 vi minus 1 is just sum of vi squared I ranging from 1 to n plus sum of vi minus 1 squared I ranging from 1 to n minus 2 sum of vi minus 1. If you look carefully, these two terms are almost equal. What is the difference between these two terms?
The initial point and the terminal point.
Yeah, but initial points v0 is 0, and terminal point vn is wt. You remember that?
Yeah.
Okay, so the only difference is the terminal term. So I may just multiply the first one by 2, and should I subtract or add the wt squared? What should I do here? Subtract or add?
Probably subtract.
Yeah, subtract. Why?
Because we counted it twice in the
Yeah,
first.
we counted it twice, but we need to count it only once. Yeah, I completely agree. Yeah. Any questions? Okay, and mn tends in L2 to t. Okay, when n tends to infinity. So I conclude that 2 sum of vi squared minus sum of vi minus 1 tends to t plus wt squared when n tends to infinity. Everyone is with me? Because we are almost on the top of our mountain we will achieve after the long climb. I don't know.
Here.
Yes.
Yeah. So the sum of vi squared minus sum of vi minus 1 tends to what?
Divided by 2.
Exactly, t plus. And now let's look at our goal. We are almost there. We are almost at the top of our mountain. In is wt squared minus sum of vi times vi minus 1, and it tends to, so it's our in. Do you remember? Final welfare, final wells minus investments. What is the limit? Woohoo! What is the limit?
Excuse me, I am a little bit confused in the last expression.
Yeah.
When
let me
we
number.
open.
Stop. Let me number them. Last
Mhm.
one. I will go first, second, third, fourth line. So I think it will be a little bit easier to work with.
When we open the brackets in the second term of the fourth expression, it will be the sum of vi squared plus the sum of vi and vi minus 1.
Where?
In the fourth, in the last line.
Yes, you may open the brackets, but what I'd like to see that I have a copy of third expression. If I look at this expression, then I have a copy of it. exact copy of it here. Yeah. So just a copy. And so what is the answer?
T plus 3vt squared divided by 2.
No, it's subtracted. You have added, it's subtracted.
V2 squared minus the thing like T
divided by 2.
Yeah. So it's subtracted. And finally, it is Wt minus T over 2. And bingo, we have calculated our first stochastic integral from 0 to T. I don't like to turn the page. Wu dWu is Wt squared minus T over 2. Rah! I have done it. We have calculated our first stochastic integral. So what was the procedure to calculate it? We have created discrete approximation. Discrete approximation can be evaluated intuitively as a profit. And then we take the limit in L2. It was a little bit tricky, but we've managed to take the limit. The unique difference between a rigorous definition and my definition that I use, for simplicity, I use equal length subdivision. But basically, we have rigorously calculated our first stochastic integral. It's interesting that the result is a little bit counterintuitive. If you consider something that is not random, if W is a non-random function, then the answer would be we would expect like Wt squared minus W0 squared over 2. Yeah, if it was non-random quantity, we would expect such value. Yeah, but it's wrong answer. We are not integrating like usual. So we see from this result that usual rules do not apply, at least partially. The integral of a sum obviously will be the sum of integrals, but some usual rules cannot be applied. Like we just take the we just cannot apply something like Newton-Leibniz formula. There are no Newton-Leibniz formula for stochastic integral. Okay, so we have done. So thank you. If you have any questions, just don't be shy and ask them. Oh, see you next time.
So
yeah.
The algorithm is to create discrete approximation, take the limit L2, and then it would be our integral, right?
Yeah. But as with integrals non-stochastic, usually we learn some basic results, and you never, so when you are required to calculate the integral from 0 to T, I don't know, u squared plus u cube du, you will not calculate a limit of partition. You just, oh, I remember the integral of u squared is u3 over 3, of u3 is u power 4 over 4, and you use basic rules to make calculations. Basically, we will do the same, but with stochastic integral. So yes, the honest definition of integral is a L2 limit of random sequences. But as with ordinary Riemann integral, almost never you take limits. You just, oh, I have some rules, and according to these rules, I can calculate.
Okay.
But the rules will be next time. Okay. So
okay,
bye-bye.
great. Okay.
Yeah.
Excuse me, I have one question about the investments. I just cannot understand why do we subtract the previous value of our welfare when we do the investments.
Imagine that your grandma left you a cup, and your grandma left you a cup, and you just hold this cup. You do not trade it, just hold it. What's the change? What's your profit as an owner of this cup? Let's imagine in the beginning, the price of a cup like this was 10 ruble. And at the end of a year, the price is 30 rubles of this cup. So what's your profit of just holding it? It's one cup.
So I just get the profit of holding my
yeah, because you can
cup.
You can let's say initially buy it for the price of 10 rubles, and after a month or after a year you can sell it for 30 rubles. So the profit of holding one cup is 30 rubles times final quantity minus 10 rubles times initial quantity, so it's 20 rubles. Okay, so profit is final welfare minus initial welfare plus or minus investments. But when you just hold one cup and do not buy cups, do not sell cups, then you have no investments in between two final points.
Clear, I understood. Thank you very much.
Okay, have a nice time. Bye-bye.
Thank you for the lecture.
Okay, thank you. Goodbye.
Thank you.